Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing distance functions. This material is produced for Ohio University Math 3110-5110, College Geometry. The topics for today are from section 2.2 of the book. I'll be discussing, as I said, distance functions. I'll give examples of distance functions, and then I'll be talking about circles. The corresponding reading is pages 27 to 29 of section 2.2, Metric Geometry, in the book Geometry, a Metric Approach with Models, 2nd edition, by Millman and Parker. The corresponding homework is this short collection, 5 problems, and only part of problems 7 and 18. Recall some important definitions from section 2.1. Definition of abstract geometry. It's an ordered pair consisting of a set of points and a set of lines that satisfy these two axioms, these axioms of abstract geometry. An incidence geometry is an abstract geometry, so again, a set of points and a set of lines, so satisfying all of those abstract axioms, but also these additional requirements called the axioms of incidence geometry. So an incidence geometry satisfies 4 axioms altogether, the 2 axioms of abstract geometry and the 2 axioms of incidence geometry. In previous videos, we saw various examples of abstract geometries. Some finite geometries, such as this one with 4 points and 4 lines, and this one with 4 points and 5 lines. We also discussed some abstract geometries that had sets of points that were infinite sets, the Cartesian plane, the Poincare plane, and the Riemann sphere. And we saw that some, but not all, of those abstract geometries were qualified to be called incidence geometries. So for example, this 4-point abstract geometry was qualified to be called an incidence geometry. But the other 4-point abstract geometry on the previous page, this one, was not qualified to be called an incidence geometry. And among the abstract geometries that have point sets that are infinite sets, the Cartesian plane and the Poincare plane both qualify as incidence geometries, but the Riemann sphere is not qualified to be called an incidence geometry. We see that there's nothing in abstract geometry or incidence geometry axioms that requires that every line have an infinite set of points on it. In section 2.2, we'll see the introduction of what's called metric geometry. We'll see that the definition of metric geometry will ensure that in addition to other behavior, every line will have an infinite set of points on it. In the current video, 2.2a, we'll learn about distance functions on a set and see examples of distance functions on some sets that we've learned about in previous videos. In the next video, 2.1b, we'll learn about rulers and metric geometry. Recall the procedure for finding the Poincare line through 2 distinct points in the upper half plane. We discussed this procedure in the video for section 2.1, video A for that section. The procedure was extracted from the book's proof of proposition 2.1.2. So suppose you're given points P and Q that are 2 distinct points in the upper half plane. If those 2 points have the same x-coordinate, then in this case, the Poincare line that they both lie on is the type 1 line, denoted that way, subscript A, capital L. On the other hand, if the 2 points have different x-coordinates, then those 2 points lie on a type 2 line, and you have to find the center and the radius of the circle that corresponds to that line. You find the center by doing this, and then you find the radius by doing that. Distance functions. The definition of distance function is very general and applies to many mathematical situations that one might not at first consider very geometrical. To say these words, d is a distance function on set capital S, means the following. D is a function, so I have to tell you the domain and the range. The domain is the Cartesian product, S cross S. So in other words, the input to the function d is going to be an ordered pair of elements in set S. The range is the set of real numbers. So that's the domain and range of the function. Now, the function has to satisfy some requirements. These three. For all p and q in the set S, when you measure the distance, you have to get a result that's greater than or equal to 0. And the only time that you ever get 0 is in the case when those two inputs, p and q, are actually the same. And finally, the distance from p to q is the same as the distance from q to p. That's a requirement for the function d to be qualified to be called a distance function. Now I'll present some examples of distance functions. The simplest one you have been dealing with for years and maybe never thought of as a distance function. I call it the absolute value distance function on the set of real numbers. I give it this symbol, so there's the symbol d with the subscript that denotes the set that it's a distance function for. So that means that the domain is going to be r cross r, so the set of pairs of real numbers, and the range is going to be, of course, the set of real numbers. And I have to tell you how it's going to work. Given two real numbers, x and y, you compute the distance between those two numbers by doing this. You just subtract x minus y and take the absolute value of the result. So for example, to find the distance between 5 and negative 3, you just compute the absolute value of 5 minus negative 3. You get the number 8. You can illustrate that on a number line as shown here. On the other hand, to compute the distance from negative 3 to 5, you compute the absolute value of minus 3 minus 5. That's the absolute value of minus 8, but the absolute value gives you a result of plus 8 again. So that illustrates that third requirement. When you find the distance from p to q, you should get the same result as when you find the distance from q to p. Finally, question C, find the distance from 5 to 5. Well, that's going to be this calculation, which gives you 0. That corresponds to that second requirement, that the distance from p to q is 0 if and only if p equals q. Now I'm going to introduce three distance functions on R2. The first is called the Euclidean distance function on R2. It's denoted this way, the letter D with a subscript capital E. Well, it's going to be a distance function on R2, so of course that means it's going to be a function whose domain is R2 cross R2. So the input to this function is going to be a pair of things that are in R2. So in other words, a pair of ordered pairs of real numbers. And the range is going to be real numbers. This distance function works in the following way. The distance between point x1, y1 and x2, y2 is computed this way. So that's the formula that you've probably referred to as the distance formula for years. But you'll see in this course that there's a whole world of different examples of distance functions. This is just now the most familiar one. This is called the Euclidean distance on R2. There's another distance function on R2 called the Taxicab distance function. Its symbol is d subscript capital T, and it's computed this way. The distance between 2 points in R2 is computed by this computation. The absolute value of x1 minus x2 plus the absolute value of y1 minus y2. And there's a third example that we'll discuss of a distance function on R2 called the max or supremum distance function on R2. It's denoted this way, the letter D with a subscript S for supremum. Now that's going to be a function that's a distance function on R2, so again its domain is going to be the set R2 cross R2, so this is going to be a function that takes as input a pair of ordered pairs of real numbers, and its range will be the set of real numbers. It works this way. To find the distance between these 2 points, you do this computation. You compute absolute value of x1 minus x2, and you compute the absolute value of y1 minus y2, and then you take the max of those two numbers. So for example, let point P be 1, 1, and let point Q be 4, 5 in R2. Find the Euclidean distance. Well, that's easy. We just use the old familiar distance formula, and we get the number 5. That's what we call the Euclidean distance between P and Q. Question B, find this. That's called the taxicab distance between P and Q. Well, we compute the change in x values, find the absolute value of that. We compute the change in the y values, find the absolute value of that, and then add those two numbers together. We get the number 7. That's what's called the taxicab distance between P and Q. Finally, find this. That's the supremum distance, or the max distance between P and Q. Well, to compute that, we find the absolute value of the change in the x values, and we find the absolute value of the change in the y values, and then we take the max of those two numbers. Well, the change in x is 3, the change in y is 4, the largest of those two numbers is 4. So that's the distance. The max distance between P and Q is this number 4. Question D, illustrate our results from A, B, and C. Well, points P and Q are the acute vertices of a 3, 4, 5 triangle whose legs are horizontal and vertical segments. So here's point P down here, 1, 1. Here's point Q up here, 4, 5. Those are kind of faintly printed numbers, so I'm just drawing them by hand. The Euclidean distance, 5, measures the length of the hypotenuse of that triangle. The taxicab distance of 7 measures the sum of the lengths of the legs of this triangle. This leg has length 3, this leg has length 4. When you add these two numbers up, you get the number 7, and that's the taxicab distance. There's a typo here. The max distance of 4 measures the length of the longer leg. So the longer leg of the two legs is the number 4. It's important to note that in all three geometries, the line that points P and Q lie on is the blue dotted Cartesian line. This line. The red and green segments are involved in the calculation of taxicab distance and max distance, but they're not part of the line. The line that passes through P and Q is the Cartesian line. It's that line. Now I'm going to discuss the Poincare distance function on the upper half plane. The symbol is d with a subscript capital H. So that's going to be a function, because it's a distance function, its domain is going to be h cross h. So this function will eat as input a pair of ordered pairs of real numbers that are in the upper half plane. And the range, that is the output, is the set of real numbers. Now, this function works in a more complicated way. Suppose you've got points P and Q that are any 2 points of the upper half plane. There are two cases. If those 2 points have the same x coordinate, then you compute the distance between them using this fairly simple formula. You take the ln of y2 over y1, and then the absolute value of that. On the other hand, if x1 is not equal to x2, then you compute the distance between them using this more complicated formula. Notice that in this formula are the constants c and r that are the constants describing the type 2 line that passes through P and Q. Remember, at the beginning of this video, I reviewed the process for finding those constants. So part of finding the distance between points in the upper half plane involves dealing with the line that passes through those 2 points, the Poincare line. So for example, consider these 4 points. A is 1, 3. I'm going to denote that as x subscript a, y subscript a. B is the point 1, 4. C is the point 1, 5. And D is the point 8, 3. Question A is to find these Poincare distances, the distance between A and B, between B and C, between A and C, and between B and D. And in all cases, give exact simplified answers and a decimal approximation rounded to 3 decimal places. Okay, here we go. Well, let's look at our first calculation. To compute the Poincare distance between A and B, we go back and look at our formulas, the x-coordinates of points A and B are the same. So we're going to use this simple formula. Since the x-coordinate of A is 1 and the x-coordinate of B is also 1, we're going to use this formula involving just the y-coordinates. When I do that, I find that the Poincare distance between A and B is ln of 4/3. That's my exact answer. And that's the only way to write that exactly. When I type that into a calculator, I get a decimal approximation. But notice that I said exact simplified answers. When you do this calculation according to the formula, you find yb divided by ya, take the logarithm of that and find the absolute value of that. Well, abstractly, that's this calculation. But that's not simplified. If you think about it, 4/3 is a number that's greater than 1. So ln of 4/3 is a number that's greater than 0. In other words, it's a positive number. So the absolute value of ln of 4/3 is just the same as ln of 4/3. So in doing these calculations and having to produce exact simplified answers, you're going to have to think a lot about some old stuff like the logarithm function and when does it give positive and negative results. Let's go on. To compute the Poincare distance between B and C, we again note that those 2 points have the same x-coordinate, so we can use this simple formula for computing this distance. It's this computation involving the log of the ratio of the y values. Now, when we simplify that, we can get rid of the absolute values, and this is our exact answer. And this is our approximation. Finally, to compute the distance between A and C, we again notice that those 2 points have the same x-coordinate, so we use the simple formula, and we get, after simplifying, ln of 5/3, which is approximately 0.511. But when we compute the distance between B and D, we have to grapple with the fact that the x-coordinates of those 2 points are not the same. So we have to use the more complicated formula, this crazy formula, to find the distance between them. So to use that formula, we have to first find C and R. So that's these calculations. We end up finding out that C is the number 4 and R is the number 5. We use those numbers along with the coordinates of B and D in this calculation, and we end up building this expression. Now we have to simplify that. That simplifies to absolute value of log of 1/6. Now remember, rule of logarithms, that ln of 1 over a number is equal to the negative of the logarithm of that number. So ln of 1/6 is the same as the negative of ln of 6. So this expression simplifies to this expression, and that simplifies to this. The exact simplified answer is just ln of 6. So again, there's a few steps of simplifying to get from here, which is what you get from the formula, to here, which is the exact simplified answer. And the decimal approximation is 1.792. Question B is to find the corresponding Euclidean distances between A and B, between B and C, between A and C, and between B and D. Well, if you look at our points, A, B, and C are all on a vertical line, the vertical line x equals 1. So we can compute their distances easily. We just find the difference in the y-coordinates. So the distance between A and B is 1, between B and C the distance is 1, and between A and C the distance is just 2. Only when we have to find the distance between B and D are things more complicated. The Euclidean distance, I should have said these are Euclidean distances. The Euclidean distance between B and D we get by using the Euclidean distance formula. We get square root of 50, that's the exact answer. We type that into a calculator to get the approximate answer, 7.071. Let's go on. Question C is to illustrate the results from A and B. Let's start by labeling the points. So those are our points. Now in question A, we found the distance from A to B was roughly 0.288. I'm going to put that in green because it's an approximate answer. And the distance from B to C was roughly 0.223. And the distance from A to C was roughly 0.311. And we found the distance from B to D, the Poincare distance, was roughly 1.792. Now in the Euclidean distance, the distance from A to B was 1, from B to C was 1, and from A to C was 2. From B to D, the distance was approximately 7.071. A couple of things to notice. Notice that the Poincare distances do not equal the corresponding Euclidean distances. Also notice that the distance from A to B in the Poincare distance and the distance from B to C don't equal each other. But do notice that even though those two things don't equal each other, their values do add up to the distance from A to C. That is, this number plus this number equals that number. That makes sense because if I look at the formulas for those distances, the distance from A to B is this, the distance from B to C is that, and when I add those up and use a rule of logarithms, I get this, which is this, which is the distance from A to C. Now this is important and it will be discussed not in the next video but in the next section when we discuss rulers some more. Okay, that's the end of that example. Let's go on. Now I should say something about the distance functions that I've presented. I've presented 5 distance functions: the real number distance function, the Euclidean, Taxicab, and max distance function on R2, and the Poincare distance function on the upper half plane. I've presented all 5 of those without actually proving that they're qualified to be called distance functions. That is, I have not proved that they satisfy the requirements that are set forth in the definition of the distance function that I presented earlier in the video. These requirements, I presented 5 things that I called distance functions, but I didn't really confirm that they meet these requirements. Well, the real number distance function, the one involving the absolute value, clearly satisfies those requirements. But what about the other 4 things that I called distance functions? The Euclidean, the Taxicab, and the max distance function on R2, and the Poincare distance function on the upper half plane. Are those really qualified to be called distance functions? Well, the book does provide a proof that one of the 4 does qualify. There's this proposition, 2.2.1, that says that the Taxicab distance function does satisfy the requirements to be called a distance function. But it's in your homework exercise, 2.2 number 1, that you'll prove that the Euclidean distance function does satisfy those requirements. And in your homework exercise 2.2 number 2, you'll prove that the Poincare distance function satisfies the requirements to be called a distance function. You should model your proofs on the book's proof of that proposition. So study that proposition and use it as a model to do the things that you have to do in these 2 homework exercises. Now, we won't bother proving that the max distance function does meet the requirements to be called a distance function. That is an exercise in the book, but I haven't assigned it, and I won't discuss the proof. The last thing I want to talk about in the video is circles. Here's the definition of circle. There's this symbol, the word circle, capital P, and a small r in parentheses. It's spoken this way: the circle with center capital P and radius small r. You get to use this symbol when you have some set S with distance function d in the discussion, and that symbol, that capital P, is an element of that set S. And that number r is a real number greater than 0. Now, what does that symbol mean? Well, it means this set. That symbol stands for the set of all points Q in the set S that satisfy this requirement. The distance from P to Q is R. So it's just the usual circle definition you've known about for years. So for example, let's consider circles in R2 using different distance functions. Question A, draw the circle in R2 centered at 5, 4 with radius 3 using Euclidean distance. Well, here's the circle. It needs no explanation. That point 5, 4 is here. There's an open circle, meaning that that point is actually not part of the circle. And then there's some obvious points, 8, 4, 5, 7, 2, 4, and 5, 1. So again, that circle needs no explanation. Question B, draw the circle in R2 centered at 5, 4 with radius 3 using Taxicab distance. Well, here's the circle. It looks kind of surprising. The center makes sense. It's 5, 4, but we should think about why the circle looks this way. It's instructive to consider why some of the points are on it. So for instance, let's consider this point 7, 5. Why is that point on the circle? Well, if we consider how to get from 5, 4 over to 7, 5, we would, if we were a taxicab, we'd go this way. We'd go over 2 and we'd go up 1. The sum of those two numbers, 2 plus 1, is equal to 3. Well, that means that this point, 7, 5, is a distance 3 from that point, 5, 4. So that point, 7, 5, is qualified to be on the circle. Let's go on. Question C. Draw the circle in R2 centered at 5, 4 with radius 3 using max distance. Well, again, there's the point 5, 4, but the circle doesn't look like what we think of as a circle. So again, it's instructive to think about why some points are on here. So for instance, why is this point 8, 5 on the circle? Well, let's think about how we get there from 5, 4. We go 3 units to the right and we go 1 unit up. Now the largest of those two numbers is the number 3. So that means that this point, 8, 5, is a distance 3 from that point. That's why 8, 5 is entitled to be on the circle. And the other points are similar. You can read this on your own. Question D. Draw the circle in the upper half plane centered at this point, 0, e, with radius 1 using Poincare distance. Well, the solution is remarkable. It's a very interesting fact that circles in H, that is, circles in the upper half plane using Poincare distance, are sets of xy pairs that also qualify as circles in R2 using Euclidean distance. So the proof of that's beyond the level of our course at this point, but it is instructive to look at this example and study what we can say about it. So the circle that's centered at the point 0, e, I'm going to do that in blue this time, with Poincare radius 1, is shown at right. It's this blue thing that looks like a circle. Now all the points on that blue circle are the same Poincare distance from the point 0, e. What's fascinating is that the Poincare center, that point 0, e, is the blue dot, not the red dot. To see why, let's consider two easy points that we know must be on the circle. The point 0, 1 must be on the circle because if I compute the Poincare distance between 0, 1 and 0, e, I compute that by doing this calculation. ln of e is 1, so I get a distance of 1. So this point, 0, 1, that blue dot is on the circle. Now think about this point, 0, e squared. Let's compute the Poincare distance between 0e and 0e squared. Well, I end up taking the log of that ratio, so again I find ln of e, and I get the number 1. So this point up here is 0, e squared, and again the Poincare distance between that point and that point is 1. And notice that e squared is around 7.5. E is about 2.7 and 1 is 1. So in terms of Euclidean distance, this point 0, comma e is going to appear a lot closer to our eyes, a lot closer to 0, 1 than to 0, comma e squared. Now an obvious question is, what is the red open dot that looks like it's the center of the blue circle? Well, that's going to be the pair on the y-axis that's the same Euclidean distance from 0, 1 and 0 e squared. This red dot appears to be the same Euclidean distance from that point and that point. Well, that means that that red dot should be the midpoint of this line segment. If we think of that as a line segment in the Euclidean plane, this red segment, we find its midpoint. It should be that red circle dot. So that means that the y-coordinate of that is going to just be the average of the y-coordinates of the bottom point and the top point. So the y-coordinate should be 1 plus e squared over 2, so roughly 0.4195. Now that number is greater than e, so that's a confirmation that that red dot, whose coordinates are 0, comma 1 plus e squared over 2, the y-coordinate of that point is greater than the y-coordinate of this point. So that's why it makes sense that that red circle appears higher than that blue circle. Well, that's the end of that example, and that's the end of the video. Thank you.